Complex architectures are unforgiving. When a localized failure point is simply covered up with a quick patch, the underlying stress doesn't disappear. It reroutes, instantly exposing 3 new vulnerabilities along the adjacent network paths. Reacting to these superficial symptoms, rather than engineering structural solutions, is the most common point of failure in technical project management. The statistician and management theorist W. Edwards Deming established a baseline rule for this exact scenario. His argument is absolute. Before you can solve a problem, you must first understand it deeply. You cannot resolve an issue that you have not exhaustively defined and analyzed. Intuition and guesswork are insufficient for modern engineering challenges. True resolution requires replacing assumption with a deterministic, algorithmic approach. This approach begins with problem analysis, a systematic examination of an anomaly's exact nature, its historical causes, and its downstream operational effects. This strict, logical discipline directly counteracts the amateur tendency to draw conclusions from mere correlated data or visible symptoms, which brings us to the core thesis of this framework. Effective management and so-called soft skills can be structured as a strict logical pipeline. This pipeline operates in 3 distinct sequential phases. We start with problem analysis, move through the 8 discipline, or 8D framework, and finish with KPI-driven implementation. This lifecycle functions as a rigid state machine, moving the system from a broken state to a verified one. Entering the first phase requires defining the strict parameters and scope of the problem. We draw a hard boundary around what is failing. With the boundary set, the next required operation is gathering relevant, unfiltered data surrounding the anomaly. This must be done before forming a single hypothesis. Massive, complex failures are rarely a single monolithic error. They must be broken down into manageable, isolated subsystems to be properly evaluated. By analyzing the system at the component level, we can isolate the specific origin point that triggered the failure cascade. This is the root cause. Once that singular root cause is isolated, the investigator must map out the holistic impact it exerts on the wider network. Pinpointing this core mathematical or operational error is a non-negotiable prerequisite. Until the root cause is extracted and measured, no solution architecture can begin. To systematically transition from that broken state to a permanently verified state, the industry standard is the 8 disciplines of problem solving, commonly known as the 8D method. The pipeline begins with D1, forming a specialized team, and D2, defining the exact parameters of the problem. D3 immediately follows by implementing temporary containment actions. This step quarantines the issue, effectively stopping immediate operational damage while the investigation continues. With the bleeding stopped, D4 focuses the team entirely on identifying the fundamental root cause driving the symptom. D5 and D6 represent the engineering core of the algorithm, developing permanent corrective actions, and then mathematically verifying their effectiveness before full deployment. The algorithm closes out with D7, implementing broad preventative measures across the wider system, and D8, formally recognizing the specialized team's contribution. Returning to the solution generation phase of D5, the corrective actions must be rigorously evaluated. This requires weighing costs and benefits, assessing practical feasibility, and modeling potential new system risks. During this final decision-making process, priority must heavily favor long-term effectiveness over any short-term relief. This highlights the critical operational distinction between D3 and D5. D3 is taping a leaking pipe. D5 is upgrading the entire plumbing architecture. Once the permanent architecture is finalized, we enter solution implementation. This is the active deployment phase, where theoretical strategies are pushed into live production environments. This icon represents a crucial transition. We are taking a static, documented idea and injecting the dimension of time, transforming it into a sequence of real-world actions. Execution begins with strict prerequisites, developing an unyielding implementation plan and establishing rigid, measurable timelines. From there, management must execute operational necessities by allocating capital and data resources, while assigning explicit, non-overlapping roles to individual team members. Deployment also demands addressing human factors. This means identifying potential logistical challenges early, maintaining clear communication protocols, and providing necessary training for the operators interacting with the new system. Even with rigid planning, live environment variables will inevitably shift. The deployment team must adapt their immediate actions without compromising the core design. Because ultimately, a mathematically or logically perfect solution holds zero intrinsic value if it cannot survive the friction of real-world deployment. Once deployed into the live environment, a solution is still only a hypothesis. It remains theoretical until its efficacy is empirically tracked and verified. Establishing clear goals creates a baseline to measure success within a continuous feedback loop. Here, we monitor key performance indicators. These metrics provide quantitative data to evaluate impact. Paired with progress reviews and stakeholder feedback, they force real-time adjustments back into the implementation plan. Continuous tracking provides the validation required to turn a deployed hypothesis into a documented operational result. However, this tracking loop is fragile in practice, frequently collapsing due to 5 distinct system errors. The first 2 errors are structural, a fundamental lack of clear quantitative metrics, and relying on inadequate technological tools that fail to capture the necessary operational data. The third and fourth errors are operational. Poor communication silos among team members naturally lead to inconsistent monitoring practices across the project timeline. But the fifth error is the most destructive: active organizational resistance to monitoring and evaluation, often driven by a corporate fear of discovering failure. Overcoming these 5 failure points is not a matter of encouragement. It requires treating the tracking phase with the exact same analytical rigor used during the initial problem definition. We start by isolating a precise root cause, pass it through the strict sequential disciplines of the 8D method, and finally engineer it to survive the friction of real-world deployment. High-level problem solving operates as a continuously optimized operational lifecycle.